In this tutorial, we will learn and discuss about geometric optics. Geometric optics is the part of optics that deals with the ray aspect of light. The goal of the tutorial is to help the facilitator of the activities with additional knowledge on the matter that will help facilitate the discussion with the students. We'll first discuss the ray aspect of light, and then we'll present the law of refraction, then total internal reflection, and the law of reflection. We will conclude on the principle of image formation by lenses. So, light is a form of electromagnetic radiation that our eye can perceive when it is in the visible spectrum. A ray is a straight line originating from a point. It represents the path along which the light energy travels. So the refraction of light is the bending of light rays as they pass from one medium to another. Rays therefore change direction. Here in this photo, you can see an example of refraction where the image of the arrow that our eyes perceive after placing a glass of water in front of it gets reversed. This is because the light rays change direction. To be able to see this reverse phenomena due to refraction, the distance between the glass, the arrow object, and eyes matter. If the arrow is placed too close to the water, we may not see the refraction as it gets very small. The phenomena can be explained using the famous Snell's law that relates the incident rays, incident angles with the refracted ray and the refracted angle by this formula, which is equals to Ni sine theta I equals to Nr sine theta R, where I means incident, R means refracted in this matter, and N is the refractive index. When the ray is incident on the medium 1 and the medium 2 interface, the rays gets refracted and changes direction. Students can then try this experience using the tools that will be provided for geometric optics. They need to see how much is the angle of refraction change with the incident angles. The surface of the interface also defines this angle, so they are advised to see it for themselves. How does the deviation changes for different shapes of glasses? So how now if we go back to the matter of glass of water, without a glass of water, light travels in straight lines as the medium in between the object arrow, our eyes is uniform. It is the air. The speed of light depends on the medium in which it travels. Given that, by adding the glass in between, light changes direction. The glass and the water have different refractive index than the air we previously had. This causes the light to change speed and hence direction. The light bends at the interface and the reverse image is perceived by our eyes. Another example of refraction is if we place a pencil inside a glass, and if we add water inside of the glass after making our observation, we will notice that light bends as it travels between water, then glass, then air to our eyes. Our object has remained the same. The refractions that is the one that is creating an illusion to our eyes. So if we take a bottle and add water in it, and we take a laser pointer, we'll observe that the light will reflect back and want to refract from from water to air. This is total internal reflection. It occurs when light is incident from a medium of a higher refractive index to a lower refractive index. Here the water has a refractive index of 1.33, while the air has a refractive index of 1. So this principle is what scientists and engineers use in optical communication to transmit signal, and also the broadband internet we have to communicate all over the world at the speed of light. So how does it work? The first signal will be transmitted and converted to an optical signal. The signal will then be transmitted inside the optical fiber by doing total internal friction, so it will go through the distance by doing this total internal reflection inside the fiber. And the optical fiber is placed under the ocean or underground. Once the light reaches the final destination, it gets detected by a receiver instrument that will encode the information from the light and translate it back to its original format, like email or voice or images. So that is how we communicate this day. Now the law of reflection is such that the angle of incidence equals to the angle of reflection. When we see ourselves in a mirror, it appears that our image is behind the mirror. We see the light coming from a direction determined by the law of reflection. So the light from here will be, so the light here will be transmitted here, and will be reflected at the same angles. So the angles are such that our image is the same distance behind the mirror as we stand away from the mirror. A mirror has a small surface that can reflect light at specific angles. So to complete this tutorial, we will now discuss how we can form an image using a lens. Students will have the opportunity to run this experiment themselves using the appropriate equipment. A lens is a piece of glass or plastic that can refract light. There are two types of lens. A convex lens is curved such that it is thicker in the middle and thin at the edges. This causes light to bind to a focal point when parallel lights are excited on its surface and get refracted, while a concave lens is thin in the middle and thick at the edges. Light which goes through a concave lens diverge as if they have come from a point which is at a virtual focal point, which is this position. So only convex lenses form real image. Concave lenses form virtual images. The thin lens equation is relying the location of where the image will be formed, given the distance of where the object is placed and the focal length of the lens. The magnification of the system is equal to the ratio of the image height and object height. So here is an animation generated from more physics to explain and understand how the image is formed by a convex lens, so that the students will be able to run the experiment themselves. So the object that we have here is we have like a focal length equal to 4, and the object is at the height distance of 2. And now the distance from the object is at higher than twice the focal length, and we get like the image is at distance 6.67 and the height is minus 1.33. That gives like a magnification of negative 0.67 and a real image and inverted image. Now if we move the object at a distance which is equals to 2f, we can see that the object now is placed at the same distance, equal distance as well, a real image and inverted, and the magnification is equals to negative 1. And if we move the object at a distance of focal length, there is no image, and the image will form at infinity. And if we now decrease the distance of the object again, and then we obtain a virtual image and image that is upright. Yeah, so here the magnification is equals to 2, and now if we move it again in the other side of the image, the other plane, and at a focal distance, there is no image. The image will be formed as infinity, and if we move it again where the distance of the object will be at 2f, and we obtain a real image inverted with magnification of negative 1. So that is how the image is formed. So the students are encouraged to run this experiment themselves with the help of the facilitator. So for any further question, please contact us.